Okay.
Yeah, Mrinal, go ahead. This is our
All right.
MLBBQ session. Mrinal Mathur is presenting.
Thank you. Thank you. So today I'm going to present this paper, a very interesting work actually. It's called the 3D Gaussian Splatting. The actual paper is name is 3D Gaussian Splatting for real-time radiance field rendering. To give you some context on what this is, so basically, like radiance field methods, they have recently been used for synthesizing synthesis of scenes, which captured from multiple photos from different angles, and they want to achieve like high visual quality, which still requires neural networks, deep learnings that are very costly to learn and render. So the while these like faster methods are like they inevitably trade off speed for quality, but in this method they want to show like we can use these rendering part even without using neural networks. Like we will be using neural networks, but not as much as what the other methods are using. So for this particular outline, we are going to look at the introduction. How did we actually arrive here? What happened? Like we will try to understand from the basics what was being used before, what is being used now, and so that is there. And we will also deep dive into Gaussian splatting. A lot of intimidating equations, but don't worry, I'll try to make it as simple as possible. We will also go through like in detail about for the algorithm that they have presented, and in the end, I will go forward with the results, and I will also show you like what type of images and like videos were synthesized using this Gaussian splatting, which will be really interesting to see. So yeah, let's move ahead. So in order to do that, let's understand the basics first, right? So, and I will give that by giving an inspiration from the paintings. So when you think yourself as an artist, but think yourself as like you're painting on a very regular canvas, right? So you're creating a space that surrounds you. You're always making sure like whatever scenery that you have, you already captured that, and you paint those colored dots for each object in the scene. And when you're doing that, you're just basically you're generating a collection of points, which we will be referring to as point cloud. Just to give an example, that's the image which which you will see if you're just putting it as a point in your scenery that you have. But now let's move ahead. I want you to visualize a very plain point cloud on a very traditional viewer, right? So whatever painting that you did with all those dots, if you look into it from a from a from a different point of view, you will see that the images are actually all correlated and they will be smooth. So those tiny dots are actually forming a picture. So this is very similar to like what pointillism is in art, where they're basically creating an image using very small and separated dots. So whenever you look uh, at that image from a distance, you will see like yeah, they are very good. But if you're going up close, you will definitely you will be seeing like individual dots that you have created. So this is the same issue, like the same issue that occurs in most of the traditional point clouds visualization techniques as well. Now imagine that you are painting like an impressionist. They don't just use the dots, they try to blend the colors on the canvas. And for what that does is like it will make the picture more smoother and more realistic, just like the image that we see from on the right side. So this is the idea between 3D Gaussian splatting as well. So instead of only using the dots, it uses the splats that are basically blend together, and these splats are are being these splats are nothing but the Gaussians that we will be seeing in the upcoming sections. So what exactly is Gaussian splatting? So in Gaussian splatting, a 3D world is represented with a set of 3D points. In fact, millions of them in a ballpark of let's say 0.5 to 5 million points. In each of those points is a 3D Gaussian with its own unique parameter that is fitted per that scene. such that it renders this scene closely to the known dataset image. The optimization and the rendering process will be discussed later. So let's focus for a moment on the necessary parameters in this case. This and just FYI, this method is not a new method. Actually, in 2001 or 2002, something similar to this was published, which is called the surface splatting, where they were also trying to use or they were trying to fit Gaussians across a surface. But I guess in that during that time, they did not really use any deep learning techniques. So it was a very traditional computer vision technique. And it's really good to see like we are actually picking up the older stuff and bringing it in our new methodology and trying to improve that as further as we go. So 3D Gaussian is at its core, it's basically just a rasterization technique. What does rasterization mean here is you want to map the 2D image into a 3D image. And how you do that is by taking like multiple sources from different angles in order to capture the whole the whole information. So for that, you should have a data which describes the scene, and also you want to draw the data on the screen as well. So this is an analogous to like triangle rasterization that we have in computer graphics, which is used to draw many triangles on the screen. And you must have heard a lot about many of the rendering techniques that we used, and for that we can use the, data points like voxels, point clouds, etc. So in this case, like instead of triangles, what we're using are the Gaussians. So they're the single rasterized Gaussian with a border drawn for clarity. So in this case, we are the 3D Gaussian is represented using three information. First is the position, which is XYZ, which determines like where each point is in the 3D space. You also have the covariance matrix, which dictates how each point stretches or scales. And I'll tell you like why that is important as we go ahead. And then we have the color, which decides like on the hue of each point, and that will be adding on the visual richness, like how we saw in the impression art. And then we have an alpha control, like alpha method, which basically controls the transparency and making the scene more lifelike. And that it also includes adding the depth in the image that we render. So how these 3D Gaussians are parameterized? We are going to use the mean with the location XYZ, covariance, the opacity, the opacity, which is basically a sigmoid function that is applied on the parameters of 0 to 1 interval. And the main important part where that is very new to me as well is the color parameter, where we'll be using these three values of RGB. But instead of using the RGB as a very basic part, we'll be using a spherical harmonic coefficient. And that's something which I think it's something which is very new to me as well, but I'll try to explain it as best as I can. Just want to pause there to ask if you guys have any questions to know. Okay.
I do have questions. I do have a question. Sorry. How do you get to XYZ from images taken at random angles at an unknown position? Or you have to have a precision instrument for this to work? The previous slide, you had the same picture. Yes, position XYZ. Where is that coming from? I only have a set of pictures, right?
Right. So you only have a set of pictures, but whenever we look at these techniques, right, we'll be taking, so just for one single picture, you'll be taking different angles. And so that is called the SFM. What's the full form of that? Wait, I know that. Yeah, structure of motion. So what that particular part does is it will so for that particular image, it will also look at the different angles from where it is taking, and that gives us an idea for that particular idea, what is for that particular angle, what are the coordinates where where we are looking at that image. So I don't know if that makes sense
So
here.
you have to know that the camera was.
Yes, initially you will have to know the location for those for that image, right?
Yeah, I'm not quite sure how to pull it off. I was thinking, like, if I take a drone with a camera and fly it around my house, taking snapshots, will you may be able to make the video? And it looks like, oh, without a GPS or some kind of a positioning system, knowing exactly where the drone was, where the camera was pointing at, it is impossible. This method will not work, right? You have to know, okay, the camera was 2 meters up at this location, at this angle, at that angle, and everything, right? You have to know the
So if you
geometry.
look at the if you look at the this app called Luma AI, right? So that also performs in the similar way, where for one object, it will ask us to take the image or at least a video or of the full object, so that we know like where the where are we localizing the object, and that is done in order to first of all understand like where what are the coordinates of those of those images in the spatial spatial information. We need we need to capture the spatial information for those objects as well. So I guess that's the reason like we need to make sure we are taking different angles for one object.
Well, what I don't understand is, does this need explicit geometry information? Or, like when we're taking a panorama image by stitching, we don't care where explicitly the camera was, because we will be just correlated the overlapping images, and by correlation, we will arrange them. So this method, does it arrange and put the images, or it assumes the precise geometric location, float 32-bit for HXYZ is given by some outside device? That's what I'm not sure. Because you can figure that information out potentially from, like, there were methods back in the thousands, potentially from just images without even knowing where they were taken from. So I'm not sure what happens in this case.
So with accurate XYZ coordinate, right, that you provided externally, each Gaussian splat can be positioned with like high precision in the 3D space. So this external data, it will eliminate the need of complex position optimization algorithm. Typically that is used in like standard Gaussian splatting. If you do want to use precise geometrical information, that allows for more accurate scene reconstruction and rendering as well. That will also be beneficial if we are in the application where we are requiring high fidelity. Um, but yeah, that's that. Yeah, that's all I know right now.
Okay, let's go. Let's sorry, we've been stuck here too long.
Okay, sure. Thanks for the question. Okay. So let's look at this particular part where why are we actually using Gaussian splatting? Because before this there were many techniques called NeRF, and NeRFs are something which are performing really well. So the existing NeRF, what it does is, imagine if there's is there a way to check this? Okay, so imagine that you're drawing some image, and from that particular image you're looking at. Okay, so we are looking at that object from a distance, right? What NeRF does, that it will start calculating the localized so it will start point yeah, so it will start drawing a ray for each pixel of the image from the sample by sampling multiple points, and it will calculate the colors and the volume density of each sample point. Now the problem with NeRF is that it will start it from the point where it's actually taking the image from the source of that from the source of that object. And because of that, you're basically wasting a lot of compute where where it might be actually just be empty. But in the case of Gaussian splatting, you're only going to look at those you're only going to consider those points where where the point ray is actually meeting, or it's going through the mean of those Gaussians. So effectively, you are, first of all, you're reducing the computation, and you are also not using all the points, because like most of the points will not be really important in this case. So that is the reason, like, why if you look into it, the NeRF is going to take a lot of time while rendering and reconstructing. But Gaussian splatting is going to definitely much faster, and it's going to perform so NeRF, just which requires up to like 48 hours of training time. In this case, it like Gaussian splatting, it renders depending on the scene for 10 just 1 to 5 frames per second. But NeRF actually renders it for 10 to 15 frames per second. So that's like a huge difference in speed and optimization as well. So what exactly are we doing here with Gaussian splatting? So Gaussian splatting has much less computational overhead from a rendering computational perspective, because it divides the image into tiles of 14 into 14 pixels, and then it sorts the Gaussians by depth for each tile. And then you'll be rendering these images by sequentially blending them from front to back. Or when I say blending them from front to back, you're basically sorting those frequency of Gaussians, and then trying to reconstruct the image as we want. And that's like exactly the image that we are seeing on the right. You will see it's not that sharp, but those all points, or those all image parts of the images are Gaussians. So how does it actually work? So we are you yeah. So first, the first part for this is we are going to use a structure of motion, where this method is used to estimate a point cloud from a set of images. And this is a method like for estimating any 3D points from a distance of from multiple 2D images. And this has been done like before as well in classic computer vision techniques, where they're using Colmap library. So if you're just going to look at the point cloud images, you will see like the image is like, just like we are seeing in the slide, is nothing but just a blob of points. And that's the image which I showed you before as well, when we were trying to paint an image, just drawing like single points in the whole scenery. And then we convert these points into Gaussians. So only the position and the color can be inferred from the structure of motion data, but we want to learn the representation as well, that because of which we'll get like higher quality results. And for that, we need to train each and every Gaussian, like that will be coming at that particular for that particular position. And then we can apply the 3D points, which can be rotated, stretched, and along any direction in the space. And that's the beauty of Gaussian, because now you're not really limited by the structure of those points, because now you can actually try to fit those Gaussians inside that view. And I'll show you like how the authors actually proposed it. So for this, in order for you to convert it to Gaussian, it could have like it could have required like 9 parameters, but they cannot be optimized directly because the covariance matrix has a physical meaning only if it's positive semi-definite matrix. So they're using nothing but a very simple gradient descent for optimization, which makes it hard to pose such constraints on a matrix directory. Directory. And that is why it is factored instead like as follows, where we're taking a sigma so we're basically taking a sigma of R S transpose and R transpose, and that's basically the covariance matrix that they have mentioned here as well. So these factorization is known as eigen decomposition of the covariance matrix. And why we want to understand this is because, first of all, S is the diagonal scaling matrix, which has 3 parameters for scaling. And R is a 3 by 3 rotational matrix, which is expressed with 4 quaternions. Quaternions. Yeah, sorry, quaternions. So the impact of this particular part is that now that we have, okay, yeah. So beauty of using Gaussians, right? It lies in the twofold impact of each point. So on one hand, like each point effectively represents a limited area in space close to its mean, like according to its covariance. On the other hand, it has theoretically infinite extent, meaning that each Gaussian is defined on whole 3D space, and that can be evaluated at any point. And this is great because during optimization, it allows your gradients to flow from long distance. So this equation which you're seeing on the right side, sorry, on the right side, it looks almost like a probability density function on the multivariate normal distribution, except the normalization term with a determinant of covariance is ignored, and it is weighted by the opacity instead. So that is the alpha of I here. So I'll go with the overview of the flow of how they're actually going ahead with like constructing the image. And we will also be looking at the algorithms in this case. So as I mentioned before, so we'll be initializing it with the structure of motion algorithm, where we'll be using the Cole map, and they can be obtained from like point cloud information as well as the camera poses. And basically these point clouds are used as initial values for the 3D Gaussian. Then you convert those points to to Gaussian by projecting onto an image plane, and so that it becomes a 2D Gaussian in that process. And this process is used so that you can update the parameters by comparing them to any ground truth input image. I guess that's where your question was, Sergey, as well. Like how are we actually um, rendering by taking different uh, point of view in that image?
So you mean Colmap creates XYZ positions, basically. It is inferred, it's not provided, right?
The Cole map?
Yeah, the XYZ positions, they are not provided by my physical device. They are inferred by the SFM algorithm.
Let me think over this. Yeah, I mean, so the points are scattered through the 3D space set, which represents the inferred position of Gaussian splats. So if and yeah, so in this case so the XYZ coordinates are being used by the Cole map. Like Cole map is just a tool to extract the XYZ coordinates by using the SFM algorithm. If
To
I mean,
infer those coordinates from flat images given in random order, right? So the input not on the screen, you start from points, but physically points do not exist, right? What exists when we start is in flat image files, right? That your camera took.
right, the 2D images.
Yeah, so 2D images. So 2D images go into some algorithm that generates those points. There's something that takes 2D images into the points, and this something does not include a guy with a ruler who goes around and measures stuff. It is an actual computational algorithm from 2D images. That's all. I think that's the case now by listening to you. That's why I didn't interrupt. So the XYZ coordinates are inferred, and I'm free to fly a drone, just take images and then put it in the algorithm and try to recreate the scenery where the drone was flying.
Right, right. So basically these algorithms, they analyze the difference between the images to estimate the camera position, and they create an initial sparse 3D point cloud. And 3D point clouds shown like in the graph are not physically measured, but they are computationally inferred from the 2D images, right? That's right.
Yeah, so I wonder how expensive is that process? Like this kind of nicely, cleanly, or shyly starts from already given points, but I wonder if the algorithm is quadratic, cubic, that it would require a lot of optimization, right, to get those points, XYZ. So I wonder, do you know the complexity of the first step before this starts?
Let me think about it.
Yeah,
So,
that's fine. That's fine. Just like let's go on. Let's just keep thinking
sure.
about
I
it.
mean, just to give you a very small answer, the algorithm, they often have like especially for this part, they often have the complexity of O of n squared to O of n cube. So they are quadratic and cubic as well, where the n is basically the number of features or pixels that are being processed. So yeah, I mean, yeah.
Unclear. You're talking about the diagram on the image
No. I'm talking about the normal SFM, basic
SFM. Okay, okay.
motion or multi-view stereo, those type of techniques.
Yeah, quadratic or cubic. That could be bad. Yeah, but they
Yeah.
probably downsample and get sloppy kind of just initial positions, and that's why we need the NeRF and other.
Yeah, I mean, so we'll be talking about the optimization process as well, in the upcoming slides. Sure. Okay. So now that we are generating the 2D Gaussians into a single image, where we are basically differentiating the tile rasterization. And the main part about this is the gradient flow, where we're calculating the loss which is generated between like the image and the ground truth. One of the things which changes and which we'll be also looking at in the upcoming slides are the optimization techniques, where the Gaussian, it changes the shape based on the gradients, and also decides on what's the color or what's the hue of those gradients should be. When I talk about hue, basically, if you look into if you just look at Gaussians as a 3D plot, you will see like it's like a cone, and on the top it's bright red, and then as you go down, you can see like the color fades, and
Are
that's
you
the
showing the right slide?
yeah. I'm at this right slide. I'm just talking about like how like what 3D Gaussians are like if you look into it in the 3D space.
Mhm.
So going forward, um, yeah. Okay. So now, the image which I showed initially, right, on this slide, we can look into it as a flow overview, where we'll be broadly dividing it into three categories. So the first part in red, it is a variable initialization. It can be like as simple, like it's simple for like code's perspective, but it is important because it is related to model design. And I'll be going with that. Like I'll be explaining that as well. The second part, which is blue, is a familiar structure in the machine learning field. So, and it is the part that receives input, performs inference, calculate loss, updates it. The third part directly deals with the Gaussian. It clones. It is so we do Gaussian cloning, we do Gaussian splitting, and we also do like removing Gaussian at specific iterations. So that is pretty interesting, and we'll be going forward with that. So the first part, so with what MSCA corresponds, they just corresponds to learning parameters, and so M stands for count. Okay, M stands for point cloud, which is obtained by SFM. The 3D Gaussian is composed of mean and covariance, and the points of point clouds are used as mean of the initial 3D Gaussian. So the 3D Gaussians are generated as many times as a number of points in the point cloud. Um, so just to give like more context in that. So basically, like in this case, the scale which is S in the first one. So scale it contains magnification information about the XYZ axis. What it does, it will convert the quaternion representation, where Q is a shape of 4 by 1, to the rotation matrix representation, where you'll be converting it from 4 into 1 by 3 is to 3. So yeah, of the shape of 3 is to 3. So after if you yeah, so after checking the source code, the initial value of S is created by taking the root of each point, which is 3:1, of the point cloud which is created by the SFM. And then you take the log and then you copy the value to create a 3 by 3 matrix. So the initial value of R is created by creating like 4 vectors of each point, and then you are filling the first value with 1 and the remaining with 0. So in this case, the A, it represents it shows the affine transform or for 2 dimensional, yeah, for 2 dimensions, where the rotation matrix is 2 by 2 in red and blue parts, and you can see how it is transformed when performing a matrix operation for scale and rotation and rotate in no change. And that's a very basic image. What do you say? Yeah, a computer vision technique where we are scaling and rotating the images without really any computation. And the same principle can be applied in 3 dimension as well. So R in this case is a 3 by 3 matrix, but it uses a quaternion of 4 variables, which is converted to a rotation matrix. So now you can actually predict four variable. So S, which is also a 3 by 3 matrix, but it has a structure that copies a vector of 3 variables. So now you can also predict like 3 variables. The reason why S, so this guy, yeah, so why S transpose R transpose is there, which is basically a transpose of R and S, is additionally multiplied, is uh, because the covariance matrix has a symmetric property, and this characteristic is created. So the covariance matrix of a general 3D Gaussian is composed of 3 by 3, and the diagonal components well represents the variance of each axis, and the other values are composed of the covariance for 2 different axes. So I know it's kind of like pretty intimidating, but I hope like if there's any question, do let me know. If for this part even I was a little bit confused. Okay, so let's talk about the optimization here. So the loss. Okay, so the first line, it simply reads the correct image I and the camera which is posing information V of corresponding image. The second line is the mean, the covariance, color, transparency, camera poses, and they're received as input, and predicted image and is created by rasterization. In the third, we're basically predicting the image and the ground truth, and we're comparing and calculating the loss. And in the fourth, basically we're updating those values by using Adam optimizer. So that's pretty simple, like how we do it in all the machine learning techniques. One thing which is very interesting. Oh, wait. It's not updating.
And you do that for each pixel, voxel, or for each tile, or like it feels like if you do it for everything, it could be painful.
Wait, so you're talking about for this algorithm itself?
I'm talking about this optimization. Yeah.
Yeah, I mean, so we are so they are doing this for each each tiles actually. So the I mean, so okay. So in the real world scenario, the number of points, as I mentioned, it can be in an order of magnitude, which is potentially like millions for complex scene. But if we were to process like each tile individually, of course the computational cost would indeed be significant, because each point they require, optimization of multiple parameters, for example, like position, color, opacity, etc. But I guess in this case, what we are doing is we're using other spatial data structures as well to organize the points and optimize the rendering. And I'll show that in the upcoming slides as well, because we are doing adaptive sampling. We are focusing the computational resources on the areas of the scenes that require more details. And as I mentioned before as well, so it unlike NeRF and all the previous methods, we don't have to consider all the points which comes in those in the direct path of our view, because unless and until it's not really passing through the mean of those Gaussians, we are not going to consider it. And that's actually an optimization technique that these authors have used. Wait, I'm not sure why it's not going to the next slide. Let me just check that. Okay, I'll just stop sharing. Just give me a moment.
Are you trying to fix your slide transition, or what's going on, Mrinal?
Yeah, so it's not going to the next slide, and I think it's stuck right now. Weird. Give me a moment. Just give me a moment.
Are you using Google Slides, or are you using?
I tried Keynotes this time, and well, okay, I don't know why it's stuck. Let me just refresh this quickly.
Apple AI figured out that the information on the next slide is so dangerous that it's so enlightened that it's a danger to the universe, so it just doesn't let you.
Okay. Yeah, just give me a moment. Let me just come back to this. Yeah, it's like my whole laptop, it just froze. I don't know why.
Yeah, Apple. Exactly. Change your thinking now.
Okay, let me just there's a workaround for this as well. Let me just check that and try to.
Reminds me my lectures during COVID. It's like nothing going on, and I have to like comment at least to have some activity. It's like I constantly talk for an hour and a half. Otherwise, the students don't say anything. It's a quiet. You can just. I came here to sit, wait. So you're rebooting the computer? It's still connected. Yeah, but the idea is here, the task, the problem is very old, right? We've seen it in 2001, 2002, when lots of people started to have digital cameras. The desire was like, hey, the classical one is Notre Dame de Paris. How many people are taking the same picture under different angles? And it's all on Flickr at the time. Why don't we just take geolocation that they're taking, the pictures are taking around the same space, and reconstruct high-res 3D Notre Dame de Paris from those images, because they were taken from all possible angles. And so this one is kind of continuation of that. And what I want is, I don't know, there are so many applications that people are not exploiting. I want to fly a drone around my area and create an official survey with measurements and everything of the property, of the boundaries and everything. Like why, like, yeah, but
basically photogrammetry. The impression that was somewhat solved problem.
It is solved if you know all of the locations and everything. Yeah, you just do triangulations and things. But no, like we're doing something that we've done with drones. Why drones were hard 20, 30 years ago? Because we didn't have enough brains, the control theory, to work with faulty cheap motors. Now those motors don't have the same rotation, they're flaky, but the control balances it out. We can now use unreliable hardware and still fly copters and things like that. So the same here. I don't want to measure anything. I want to just take any camera, just do this, like a video, reconstruct 3D view from that. That's the beauty of that. So Mrinal probably was rebooting and it disappeared. But so far the demos I've seen only predefined. It's not like you do it. Have you seen the demos that you can actually use?
It's
But it's demo, it's like fixed.
yeah.
It's not like brain chop, drop your brain and run it. No, it is like, okay, whatever we give you, look at it.
Yeah.
No, but I want to do it right here.
I mean, yeah, startup demos are all like that. We should have one data center in space demo. That one is hilarious.
No, but it's again not a demo, it's a video.
Yeah,
And
it's a
I've
video.
seen Star Wars.
All right.
Okay. Oh yeah, yeah. Color cons. That's what it like. Yeah, my brain is expanding. What are you showing? That slide that was prohibited by Apple.
Oh wait, don't tell me this is.
No. I'm. It's my terrible try to imitate one of the scenes from Adventure Time. I mean, every second of Adventure Time is like that. It's like drama. My yeah, sorry.
Okay.
One of my kids watched all 11 series in like one sitting, day after day after day after day. And I was like, oh, and not again, not again.
Okay, I don't know what's happening here. Okay, stuck again. Just
At least we see a picture now. Before we saw just the name.
Is that a splatted rendition picture?
That's how we know Gaussian Splatting fan by looking at your avatar.
I'm just trying to okay, yeah, I'm just trying to connect it with my other laptop. Just give me a moment.
That's a good neural cell transfer. You can.
Trying again.
All right, okay. Sorry about that. So I'll just try to quickly go over it now. Okay, so the optimization which I was talking about before, right? So whenever any Gaussians they were, so let's say you have this particular image, which is kind of a random image, and you want to fit the Gaussians using, let's say, the gradient descent in this case. Now what happens most of the cases, so in the below image, if you look into it, many times the Gaussian will be so it will be overfitting with that image that it will be covering the whole image, and that's a problem. So that's the reason what these guys they propose is they will be splitting those Gaussians into two or more in order to fit into that particular image, so that it can be like as small as possible, and then you will optimize it in such a way that it will be yeah that it can be stretched or rotated in such a way that it will cover the whole image. And that actually the strategy of periodically setting the alpha value to 0, it plays a large role in controlling the overall Gaussian as well. So this is one of the most interesting optimization that they have done in this paper. For rendering, okay. So the covariance in this, okay, so it is launched once in a while during training, say like every 100 stochastic gradient descent step. It it will try to address under and over construction, and it's important to emphasize that the gradient descent on its own can only do as much as like just adjust the existing points, but it would still struggle to find good parameters in areas that lack points altogether. Okay. So that's where the adaptive densification comes in, where you're splitting the points with larger gradients and removing the points that have converged to a very low value of alpha. And in this case, after initializing a very simple stochastic gradient descent, it is used to fit everything properly. So the scene is optimized for a loss function that is combination of like L1 and DSIM, which is the DSIM in this case is a structural dissimilarity index measure between the ground truth and the current render. But that's not that's not it, because another crucial point remains, and that's the adaptive densification, which I just mentioned before. And what that adaptive densification is, it's nothing but sorting it. So you are rendering the so you're basically rendering those each pixel, and it can be reduced to an alpha blending of pre-ordered points from the tile from the tile to pixel which it belongs to. And that so what that does is, it will, first of all, it will smoothen the Gaussian. That is, smoothen the Gaussian, and it will also make sure, like, wherever the Gaussian is over parameterized or over generalized, it will try to it will try to split it or clone those Gaussians, and then do the steps where it's going to fit in that particular image as best as it can. Now, if the Gaussians are not optimized, like, okay, so that's a very simple question, right? Like, how is it even possible to get a decent looking image from, well, like, a bunch of blobs in space? Well, it is true that Gaussians aren't, if the Gaussians aren't optimized properly, you will get all kind of pointy artifacts and renders, and I show that as well. So they look quite like ellipsoids, and the key of getting good renders is three components: the good initialization, differentiable optimization, and the adaptive densification. Like all those methods which we discussed before this. So so in this case, for point location on the means, the authors propose to use a point cloud which is produced by SFM. And since the SFM, they produce like a sparse point cloud as a byproduct, why not use it for initializing? When the point cloud is, it's not so the logic is that any 3D construction, right? Like, let's say NeRF or something more classic, you must know the camera matrices, so that you would probably run SFM anyway to obtain those. Since SFM produces a sparse point cloud as a byproduct, we can use them for initializing. So that's what the paper suggests as well. When the point cloud is not available for whatever reason, that's important, a random initialization can be used instead, but that's under the risk of potentially, like, a potential loss of final reconstruction quality. I'll just skip over this right now. And yeah, so I'll go with this spherical harmonics, which is pretty interesting. So
We have
that's what
like 5 minutes, Mrinal. I don't
Yes.
know.
Yeah. So one thing which so basically what we are doing here, we are trying to we're trying to get the colors or the hues for those particular Gaussians and the pixels. And let's say, so we have like each color, red, green, and blue, and in a linear combination of the first uh spherical harmonics function. And this is the function which they have proposed. It looks very intimidating, but in this case, let's say the L, if it's equals to 1, then the overall equation, it boils down to a very constant value, which is 0.28. And on the contrary, like for higher values of L, it produces more complex surfaces. And that is, it might, I mean, for me, I thought like it's going to be that's simple, but apparently it's not, because in order to optimize this particular part, you have to like you have to make sure like all the parameters are correctly initialized. So yeah. Oh, okay. So I'll go over the evaluation metric in this case. So as you can see from their section, which is 7K and 30K, the all the three evaluation metrics that they have used, it's the best among all the other methods that is present in the market right now. So especially NeRF 360, which was supposed to be the best, but now you can see like so SSIM value is significantly larger than all the other techniques. And for LPIPS, it's the lowest among all the techniques that they have used. Actually, rather than me showing this, I will go ahead with the main part, which I wanted to show you, which I'm very excited about. There you go.
You're not sharing. Okay.
Yeah. So this is what the Gaussian splatting is rendering right now. If I look into it, if I just go as deep as I can in this, you will see that each Gaussian. So if I look into it as a part of just like a small blob, you will see like they're nothing but like very small, sharp, specks. And those small specks are nothing but the Gaussians in this case. But if you look into it from a distance, you will see that it's really generating that image or rendering those images perfectly. Even the leaves, the whole scenery, that's perfect. And so these shards, this is what I was talking about. These shards are nothing but like Gaussian values. And these Gaussian values, since they do not really have any information with the ground truth image, so they are being initialized randomly. And whenever they are being initialized randomly, you can see like there's nothing. And so since it's a huge space, it's a huge 3D space, unless and until you render that particular image in that in a very specific 3D point, you will yeah, by that I mean like all the other space will be empty, and that's the reason you are seeing black in that case. But as soon as you look at the actual ground truth or the actual 3D point where that initialization has happened, you will see the rendering done properly. And so that's pretty interesting. So these all points, these all sharp points are all Gaussians, like of different hues, different like different optimized techniques. And yeah, as you can see from this, like there are like millions or billions of these here. We can't even count it. So yeah, so this is like one of the examples, which is pretty interesting. So yeah.
Have you done it to your room, or can you do it, or it's just predefined demo? That's it. That's
No,
all
this is a predefined demo. I haven't tried it for my room, but I mean in this in this website itself, they have like a lot of a lot of examples. Just if I look at just this particular Ford is as well, you will see like this is just an image, but if I go closer to this, you will see like all these Gaussians, all these shards are there. And yeah, if you just look at one point, it will not make a lot of difference. But when you look at from a distance, you can see an image which is sharp, which has proper detailing, and it changes. So one thing which about this is the Gaussians will try to adapt the colors as well as the scenery by if you're moving from one point to another. And the best part about this technique is also like since we're using the Gaussians, you can take this whole image, like this whole car, and you can shift it around across the scenery as well. And the Gaussians will adapt on its own. But that the copy pasting and editing of that image in itself was not available in NeRF or any other rendering techniques, because for that you will again have to retrain the image in order to create that particular scenery. So
Do that?
sorry.
Is there a demo where you can do that? Copy paste a specific object?
I was trying to find that demo, but unfortunately I didn't see that. But for a lot of tools like Adobe, they're using this technique as well. So that's how I know like they can do this.
So I can think of many applications for using this as an instrument for this or that. But can you think or anyone about where in science or like where in our research as a tiny place in science we can use it, but anywhere like for advantage? Because again, it's a good instrument, mapping instrument, right? Geometrical map from.
It reminds me of RBF kernel with support vector machines, like just like instead of the mini Gaussian thing.
No, but as a tool, right? It creates from flat views, it creates. So can we use this for CT instead of radon transform or something like that? I don't know, like, get images. Well, CT goes, it's a projection of everything in the field of view. But yeah, why are you interested in this,
For
Mrinal?
brain images, I'm I have not really seen this application for 3D brain images. But yeah, I mean, I don't know. So if you this part would mainly be used for visualization, right? In order, I mean, this is something which we have been doing since a long time, but we are using point clouds and voxels. So maybe you can try by using this technique as well, because I mean, Gaussian splatting can be used to generate new projection views for CT scans, right? And I mean, this is particularly useful when you have like limited projection data, but you need to reconstruct a full 3D volume is what I'm thinking. So, but I guess I did see some research happening on this. So that was called Gaussian splatting for CT, and that was developed for this particular purpose.
Yeah, I think DMAP talk is starting next door, like 5 minutes ago. So why don't we conclude here? And thanks, Mrinal. Sorry about the difficulties with.
Yeah, sorry about that, guys.
Yeah.
I'll share the slides as well. It's
Very interesting, and I will ask you questions later about why you are interested in this.